I think I'm ready to get started. It's not quite time, but I think everybody's here, so we can get started a minute early. Welcome to Theory of Computation. My name is Professor Stecker. I'm glad to be here. I really like this class. Of course, everybody likes every class, but I think Theory of Computation is near and dear to my heart. So I'm glad to be here. I hope you're all glad to be here. Let's just check out the syllabus briefly, and then we can get down to some business here. So you can see at the very top. This is annoying, but on Wednesdays, our class meets at a different time and in a different room, 204, which actually I think is a nicer room than this one. But yeah, I know it's confusing, so go over to that one tomorrow. But then not on the other days. You can see at the top here my email. That's the best way to get in touch with me. My office is in Banno, the ground floor, number 17. Check it out. It's a little hard to find those offices in the basement if you haven't been there before, but come on by. My office hours are listed here, 11 to 12:30 on Tuesday and Friday, and Wednesday 10 to 1. So this is always like the 2 hours or so right before class. So I hope that's convenient for everybody. If you don't like those times, if you're busy or whatever, I'm happy to get together by appointment otherwise. And it says office hours are in my office or by Zoom. So if you don't want to come down to my office during those times, I'll just be sitting there, and I'll have my Zoom thing turned on so you can connect that way if you prefer that. Sometimes I forget to turn the Zoom thing on, but I get a notification, like if you come and I'm not there, just wait a few minutes and I'll probably show up. All right. Our final exam, you can see, is Tuesday, May 6th at 11:30, so put that on your calendar. And the QR code here is for the class website. This is because I don't really like using Blackboard, so I'm not going to be putting anything on Blackboard. It will all be put here, and all is not. There's not going to be much. You will principally go there to see the homework assignments. But if you go to Blackboard for this class, you will see, I think, just a link to send you to this other page. So that's that. The textbook is, I meant to bring mine to show it to everybody, but it's called Formal Language, a Practical Introduction. We will be using the textbook mostly just for the homework problems, so I'm not going to ask you to read the book. So if you have a friend that you can share with, that'll be totally fine if you don't have the book yet. You didn't hear this from me, but I've heard that some rascals out there have been able to find a PDF of this book online by doing fairly simple searching for it. So if you don't have the book yet, you may consider your options. All right, let's talk about the class description here. I'll just read. This is I didn't write this stuff. This is the official description from the book. This course explores what computers can and can't do by examining simple mathematical models of computation. Topics include finite state machines, regular expressions, non-determinism, push-down automata, context-free grammars, and Turing machines. We will see that there are limits to what computers can do, and in doing so, we will learn about what a computer really is. You may be surprised, huh? That's gives you some idea of what the course is about. So the class is about computation from sort of an abstract point of view. So we will not actually be using computers. Like, I'm not going to ask you to write code and that sort of thing. It is more about the idea of a computer and what are the capabilities of a computer. And I don't mean like your specific computer. Like if you have a Windows and I have a Mac, they have different capabilities. But that's not what I'm talking about. I'm talking about just computers in general, the idea of a computing machine in general. What are the capabilities of such a thing? And I think you may be tempted to say the simple answer is, aren't they capable of anything? That's kind of the point of a computer, is that it can do anything. You can tell it to do whatever you want and it will do it. This is, more or less, that is the case But there are actually certain things that no computer can ever do, no matter what. And it's not, and I don't mean things like, a computer could never truly love or something like that. I mean, like, there are actual specific, like, mathematical things which a calculating machine cannot calculate. And so that's kind of the overarching theme about this course. So, like, we're not going to talk about that specifically every day, but that is one of the big ideas that we're going to discuss in this class. So I hope that sounds interesting. To me, it's very interesting. It's especially interesting to me, maybe I will get slightly philosophical here. It's especially interesting to me if I'm saying we are going to talk about the abstract idea, not just of a specific computer, but of any possible computing instrument that you could imagine. Depending on your particular beliefs about the real world, when I say any possible computing instrument you can imagine, probably this includes the human brain. And so when I say there are fundamental mathematical limitations to any computing machine, these things also apply to human brains or people as computing machines. I mean, you could debate about, is a person really just a computing machine? I would say, I don't know, but at least like a brain is a physical object and it does things like computing. And as such, as a physical object that does computing, it is subject to certain hard mathematical limitations. And this to me is very interesting, not only as a mathematical fact, but as a fact about sort of me as a human being and my place in the universe. There are certain things that are just straight up impossible for any kind of computer to do. Very, very interesting to me. Anyway, that's my sales pitch. I hope that this seems like an interesting thing to talk about. I got my computer here. That's because I am, using the screen, and I'm going to be recording class every time. So I'm recording video, I suppose, not like with a camera, but just this, what you see on the screen, and the audio. And I'm going to, after class every day, I'm going to post that on YouTube. So please like and subscribe. This is just so that, like, after the fact, if before a test or whatever, if you want to go back and see something again, you will be able to. And of course, if you miss class, you can check out the recording. I'm also going to take just what you see, and I'll package that as a PDF too. So if you want to just see the notes again, I hope that that's helpful for everybody. And you will see, once I start posting those, you will see them appear at the class website here. So check them out. I like just in general, when I'm teaching my classes, I like to make sort of everything available to whoever, like you guys, of course, and also, any random people on the internet, which is one reason I don't really like using Blackboard, just because it's sort of locked down behind you got to log in or whatever. All right, let's just talk about some of the details. The class, like your grade in this class, is made up of homeworks, quizzes, and tests. So this thing about the homework, it says the homework will be assigned each week, and the homework is going to be due each Wednesday night, not including tomorrow, but I think probably by the time we get to next week, that's enough. We will have done enough to have our first homework assignment. And like I said before, the homeworks will generally be taken out of the textbook, although sometimes I'll make up some of my own problems for some of them also. All right, it says, It says students are encouraged to work together on assignments, but you each got to hand in your own papers. I really mean it. You can work with your friends, and if you and somebody else are doing the homework together, and you turn in stuff where you're writing like exactly the same answers, that's fine with me. I will leave it up to you to sort of be responsible about freeloading off of your friends. If you are copying your friend's homework every week, you may do okay on the homeworks, but you will do terribly on the quizzes and the tests, so don't do that. That's about the homework. It says all of the assignments will be handed in electronically at Gradescope. This is an electronic homework sort of thing that I hope that everything goes smoothly using the Gradescope. I'll say a little bit more in a bit about Gradescope specifically. It says late homeworks without excuse will lose 1/3 credit for each calendar day. So them's the rules about the homework. All right. And then the quizzes. It says at the beginning of each class on Friday, a short quiz will be given covering that week's material. So the idea is every week there is a homework due on Wednesday, and then that stuff that was on the homework due Wednesday will appear on a quiz on Friday. It's not a lot of time in between, but I'm trying to sort of keep it moving. The idea is the quiz is not supposed to be some kind of big deal. If you, the quiz will be just like 10, 15 minutes at the beginning of class. We do the quiz, and then we go on with the rest of class. And the idea is that the quiz questions will be very similar to the homework questions. And if you did the homework on Wednesday and everything seemed fine to you, then you should do fine on the quiz without any kind of extra extreme effort. So that's the idea with the quiz. No calculators on the quiz. This is not really that kind of class. You're not going to want a calculator. So no calculators on the quizzes. All right. On the flip side, you see something about exams. There's going to be 2 midterm exams. That is like 2 exams sort of during the semester, during our regular class time. And there you can see the dates, February 21st and April 4th. Those are 2 Fridays. And students will not use calculators on the exams. And as far as so we have 2 exams during the semester and then the final exam at the end. And it says the 2 midterms are weighted equally in your grade, and the final exam is weighted double. Right? The final exam is cumulative, but the midterms are not. I will remind you of all of this later on. So it's the homeworks, the quizzes, and the tests, and that's basically it for your grade. Here's something cute. For the grading, choose your own ratios. You have the 3 categories. They each will get averaged together somehow, and I would like for each of you to decide on your own. We're not going to vote about this. I mean person by person, you can pick how much do you want the homeworks to count versus the quizzes versus the tests. There are rules, of course. So I say sometime on or before February 7th. I'll remind you of this when it gets closer. I just want you to email me and tell me what your preferred ratios for the 3 categories are. And the rules are, first of all, give me 3 percentages. They should add up to 100%. Each of them must be at least 30%. So you can't just be 0 on the exams because you don't want to get stressed about the exams. So you can't go below 30, and you can't change your mind later. After the date of February 7th. All right? So think about it. Think about sort of the how you would like yourself to be evaluated, really. The homework is kind of like you have essentially unlimited time to do the homework. It's not unlimited, but it's there's no real time pressure when it comes to doing the homework. The quizzes, there is some amount of time pressure, but it's very focused. Every quiz is only 1 or 2 questions, and so you can really focus in. And then the exams are a little more broad band. So think about it. Decide for yourself how you want to weight each of those 3 categories, and let me know eventually. And it says if you never notify the professor, you will default to exactly 33% for each category. This is because I've done this in other classes, and sometimes people just never tell me. And I'm not going to try and I'm going to remind you. I'm not going to try and make you forget. But it annoys me when people never tell me. So if you never tell me, I'm gonna set you at 33%, exactly 33%. I don't mean 1/3. I mean 33%. So it'll only add to 99. I screw you by 1 point because you didn't tell me. So just tell me. All right. Any questions about any of that? I hope this seems
For exams for the choose your own ratio, it's the 2 exams together.
And the final exam.
Okay.
Yeah. So all of those together would get this particular weight in the average. Yeah. All right, great. Let's talk a bit. So there's a thing here about my office hours, which basically just says, I hope that you will feel free to come to the office hours and talk about the homework or whatever else. This is not something which is only there for the benefit of people who are doing really badly. Certainly, if you are really struggling, you should definitely come and talk to me about it. But even if you're, doing well, I think some of the things that we talk about from time to time will be difficult, and it doesn't reflect badly on you to come and chat. That's part of how this whole thing works. And then at the end there, a little note about counseling services. I hope you're aware. We have free counseling services. Can you believe it? Get your free health care while you can. I have found counseling and such things to be helpful in my own life, so I hope that you check that out if you ever feel like you want to. Sometimes I talk to my wife about something, and she says, maybe you should talk to Stacy about that. I think, yeah, maybe I should talk to Stacy about that. Stacy is not my wife. All right. Great. I think that's all I wanted to say about the syllabus. I would like just to take a few moments to make sure everybody is cool with the grade scope. So I don't know if you've used this before, but you should have gotten an email this morning when I set up all of your accounts on Gradescope. The way it works is you are going to write, so you're going to do this for the homeworks, and you should do all of this on your phone. I think it's easier to just do it all through your phone rather than using a computer. But the way it works is you're going to write your homework problems or whatever on paper like you normally would in a typical math class, and then you submit by taking pictures and sending it into Gradescope. If you like to write on an iPad or something, that's fine. You can do screenshots, or sometimes I often get submissions of phone pictures of iPad screens, which is all right. It's fine with me. Anyway, what I'd like to do right now is just to try doing this. I want to make sure that everyone is able to connect. So if you get out your phone, I have created a dummy homework assignment in the Gradescope. And all it is, so if you are able to log in, you should find the email that they sent, and hopefully that has a link or something by which you can go to Gradescope and log in. And there is something called dummy assignment. And I would like for you to just tell me something interesting about yourself. So you should write down on a piece of paper or on something you can take a picture of, and then submit that through the Gradescope for this first assignment. This is not, for credit or anything. I just want to make sure that everybody is with it as far as the Gradescope goes. So take a moment and see if you can figure it out. I'm going to walk around just to make sure everybody is doing okay. If you're having problems, hopefully we can work it out right now. And if not, it has to be worked out before our first real assignment, which will be next week. everybody seems to be doing all right. I'll give you another couple minutes to get it going. All right, I think everybody worked it out, or at least got somewhere. Like I said before, it doesn't all have to work out right now, but sometime before Wednesday will be our first real assignment. I mean, next week we should work this out. Please, if you're still unable to log in, maybe try again later, but also talk to me if it doesn't work, and we'll figure it out somehow. All right. I think I'm ready to get down to some business. Let me just say, as far as like this class, taking notes or whatever, I would suggest that you write stuff on paper, or I mean by hand. Like trying to type out what I say is going to be more or less impossible. There is going to be a lot of sort of simple diagrams that look, kind of like this. Stuff like this, we're going to draw little pictures like this all the time, which will be very hard to keep up with if you're trying to design them on your computer somehow. So, I don't really care how you want to live your life, but this is my suggestion for this class in particular. By way of introduction, I want to talk about one of the most famous kind of ideas in the history of the theory of computation. This is called the halting problem. Maybe this is something you've heard of before. I don't know. The halting problem. This was one of these sort of original questions that motivated the theory of computation, although it seems a little more reasonable to us today. So I'm going to kind of phrase this in more modern terms, but this is the kind of thing that people started thinking about at the beginning of the 20th century. So this became, I will say, a big idea around 1900, and it was eventually solved, or sort of fully worked out and figured out by Alan Turing, who is sort of the big name in the theory of computation, at least the early days. Turing has been described as sort of the inventor of computer science, you might say. The father of the computing machine. He created, he himself was not an engineer or a manufacturer, so he didn't make a lot of machines, although he was involved in some of that. But really, Turing was the first person to have the idea of a general purpose computing machine. Like in those times, in the early 1900s, there were calculating machines like cash registers and simple mechanical calculators with gears in them, but they were built for specific purposes this machine is for adding, and that kind of thing. But Turing had this idea that like there could be a machine which he referred to as the universal machine, which in theory could do anything, and that was its purpose was not to do a particular thing. Its purpose was you could reprogram it to do whatever you want, and that's basically what our modern computers are. He called this concept, he called it the universal machine. Nowadays we refer to this concept as a Turing machine, which is, I mean, in modern terms, we would just say any kind of reprogrammable computer, a computer that doesn't have a specific task that it does, but it is reconfigurable to do whatever you want. And now we have these, we carry them in our pockets at all times. Anyway, one of the original sort of mathematical problems that was considered in this area, of course, in the early days, this was just a purely mathematical thing because universal computing machines didn't exist until like the 1940s or something. So this is called the halting problem. Like I said, I'm going to describe this in modern terms, but this is about when you write code. I'm gonna show you some examples using Python. When you write code, of course, you write your code and then you try to run it through a compiler or an interpreter, and like most of the time it doesn't work because you did something wrong, and then you go back and try and fix it, and then you keep on trying over and over again. But the fact is, like, a compiler or interpreter, whatever it is you're using, will detect errors, right? If you like misspell a built-in word or something like that, it'll just say, no, you can't do that. And then hopefully you'll be able to fix it fairly easily. That's a certain type of error that is easy to detect if you just misspell the word for or something. There are certain kinds of errors that the compiler will not be able to detect, like if I want to write a function that, say, multiplies a number by 3, but instead of 3 I put a 4, that's an error because it's not doing what I want it to do, but there's no way for the computer to know that that's not what I intended. So there are certain types of errors which are not possible for the computer to detect because maybe I just wrote something wrong. Another type of error is, what about infinite loops? And that's what the halting problem is all about. Infinite loops are tricky. I know you've all at least had some experience with programming. Have you ever seen, you try to run a piece of code and the compiler says you can't do that because this would cause an infinite loop to happen? This probably is not something that you've ever seen before. Of course, it's not hard to write some code which makes an infinite loop happen, but generally speaking, the compiler is not going to stop you from doing that. So I have an example here, and I hope that my recording setup here does not play well with my showing you my screen, but I'm going to try my best here. So, can you see this? Yeah, all right. So what I have, not that, sorry. I thought I had this already, but these are just random other things. All right, there it is, all right. So here is a very simple bit of Python code. I define a function called loop, and it says while true, pass. Does anyone know what pass does? This is an obscure Python function. When I tell you what it does, you will know why. You've never heard of it. Pass just does nothing. It's just a way to say don't do anything. And it just goes on to the next line. In this case, it'll just continue this while loop. While true means do this stuff over and over again as long as this is true. And since it just says true there, it's just going to do it over and over again forever. And pass means don't do anything. You need pass here because if you took this out, if you just don't write anything here, it'll say there's an error because there's nothing inside of your while loop. So you have to put that there to make it actually do something. Anyway, this is the function, and then I say do the function loop. This function will just go forever. It's never going to stop. And I have a little, hope you can see this. This is my terminal window here. If I run this through my Python interpreter, it's called loop.py. Check it out. I'm going to hit the button. You see it going? So it's now going. It is going through this loop over and over again, and it's never going to stop. And what I'm trying to point out is the interpreter, when I did this, it did not try and stop me and say, hey man, this is not gonna do anything for you. The only way to make this stop, I can sort of kill it right there. Keyboard interrupt. All right. So infinite loops, the compiler does not attempt to detect if there's going to be an infinite loop. Even though in this case, it's actually, I mean, it wouldn't be so hard to analyze that code and realize, like probably ChatGPT could tell by looking at this that it's not going to ever stop, right? So it is possible to do that kind of analysis, but the compiler doesn't. All right, and so the big question as far as the halting problem goes, maybe I'm going to try and write something else on my, this might go all crazy. Yeah, it's a little crazy, but I'm going to say infinite loops are tricky here. The big question is, can you still see this? Can we make an infinite loop detector? Some kind of piece of software which could, like before I run my code, it would analyze the code and tell me if it's going to loop forever. This actually would be very useful in real life if such a thing existed. Because then you could build that into your compiler, and the compiler would be able to tell you ahead of time if it's going to make an infinite loop or not. Infinite loops are, generally speaking, undesirable. And usually, like when you're using a computer or something and it freezes up and you have to turn it off or whatever, that's because of an infinite loop. Like that's why it froze. It looks like it's not doing anything. Actually, it's usually when that happens, it's not actually not doing anything. It's sort of stuck in a rut where it's trying to do the same thing over and over again and it's unable to do anything else. So it would be very useful to make an infinite loop detector. In the old days, they didn't have programming languages. They referred to this as the halting problem, as an abstract mathematical question about, is it possible to look at some kind of procedure and decide ahead of time if it's going to run forever or if it's going to halt? That's why they call it the halting problem, all right? The big answer, and I will just give you, this is a little spoiler alert, Turing said, and Turing was actually the first person to demonstrate this, no, it is not possible to make an infinite loop detector. This is one of those things that on its surface, it doesn't sound all that complicated, but actually, if you think a little bit more about it, you will realize actually it would be totally crazy if this was possible to do. So I don't know, like if you just ask someone randomly, someone who knows a little bit about programming, hey, do you think it'd be possible to write an infinite loop detector? I would say on a surface level, I feel like maybe that would be hard, but I don't know about impossible, right? I'm going to try and convince you, we have 18 minutes remaining. I'm going to try and convince you that if such a thing could possibly exist, it would be totally crazy. Like that actually, when you think about it in more detail, you should realize such a thing really should not be possible. And I have another bit of code here to share with you. I'm going to have to go back out here, sorry. All right, this is quite a bit more complicated. Bunch of stuff, but actually it's fairly simple. It just looks a little complicated. I would like to tell you a little bit, maybe I'll switch back here for a moment. Sorry, I'm not usually going to have like several windows open, so this, okay. I'm going to tell you a little bit, this is a little mathematical diversion. Something called the perfect box problem. This is an old problem that was considered at least as long ago as Euler, like in the 1700s. So this is a classic kind of a mathematical problem that people have been considering for a long time. And it is related to, everybody knows about Pythagorean triangles, Pythagorean triples. I mean like the old 3, 4, 5 triangle, that kind of thing. This is a special triangle in which all three sides have a whole number length. And that's only possible if those numbers are just so. Like if I change this to a 4 also, then they won't all be whole numbers, right? There are only certain numbers that work to make a Pythagorean triple. The perfect box problem is there a 3D box sort of looking like this? A three-dimensional thing, right? Where all the sides and all the face diagonals are whole numbers. Such a thing would be called a perfect box. All the sides and all the face diagonals being whole numbers. Anybody heard of this before? You know an example? Now, if I ask you, is such a thing possible or not? It's not hard to write a little bit of code that will try to answer this question for you. And that is what this, I suppose, slightly complicated bunch of stuff is doing. So what it's doing here, I'm not going to try to explain every line here, but basically we are making all possible triples of numbers. These represent the 3 dimensions of the box. And then it's just going to check, do these 3 dimensions make it so that the diagonals are all whole numbers? And the way you check that is by doing these kinds of things. This is like the Pythagorean theorem to get the length of the diagonal and say, is that a perfect square? And if it is a perfect square, then that means that the diagonal there is also an integer. Anyway, what I can do is, so I define this function called perfect box. Keeps on checking until it finds a perfect box. And I'm going to go to my terminal here. So I'm going to say, if you care, I'm going to post this code on the website if you like. So what it's doing right now is checking all possible dimensions of those 3 sides and seeing if the diagonals all end up being whole numbers or not. It's checking these values of m's that you see there. Like for m equals 300, it checks all the sides where the 3 numbers add up to 300. And then if that doesn't give you an answer, it goes up to the next one. Hey, there it is. You found a box. That's perfect timing, isn't it? This is like, oh, I was just thinking of those numbers, right? It turns out those are the smallest 3 numbers that you can use that actually make this work. I don't know when this was first discovered. I think people discovered these 3 numbers without using computers. But anyway, that perfect box thing, it is really possible. And those are the 3 smallest dimensions that make it work, all right? Now, I'm going to make it a little bit more interesting. Actually, what I've been talking about is not typically what we call the perfect box. The perfect box is one in which all those diagonals on the faces are whole numbers, and the diagonal going through the middle of the box, the solid diagonal, is also a whole number. So I had just a slight variation of my code which will do that. So here, if you notice, I was running a function called almost perfect box. This one, the real deal, is the true perfect box, which additionally has a whole number solid diagonal through the middle. And I'm going to run this code again. So it's not going to find anything, certainly, until it gets to 401. But that one, 44, 117, 240, it turns out the solid diagonal through the middle is not a whole number for that one. So that one is not good enough. Anyway, I can run this code and try. It is, again, verifying, or it's trying to search for dimensions which give you a perfect box, all right? This time, I'm not going to try to wait until it gives me the answer. I'm here to tell you, this is the interesting twist about this whole story about the perfect box. Like I said, Euler tried to address this problem. The question, does a perfect box exist or not? That is, what? This is the same one. I forgot to save my code. This is a rookie mistake, sorry. You gotta save before you run it again. All right, sorry about that. The question, does a perfect box exist or not, is actually currently unknown. Nobody knows if there is an answer to this question or not, all right? It is, one of the sort of big unsolved problems in, this is something we would call number theory because it's about sort of basic operations of whole numbers, but it's extremely hard problem to try and solve. Now, what does that mean about this program that I wrote? Do you think it's going to stop anytime soon and say, here's the answer? Probably not, because actually nobody knows if there even is an answer or not. And surely in the past 300 years, somebody has tried this, what I'm trying right now. So I'm not breaking any new ground by running this code here, all right? What I'm here to tell you is, I'm going to go back to my screen here if I can. So my code that I just wrote, so my code if a perfect box really does exist, then it will stop, right? And print out the answer, just like it did before. But if it doesn't exist, if no perfect box exists, which may be the case, like maybe it's just impossible to make a box with all those perfect dimensions. If no perfect box exists, my code runs forever, right? Because that's all it does is it keeps on checking forever. And if it never finds anything, it's just going to keep on going forever, all right? If no perfect box exists, then my code runs forever. Now, again, I would ask you to consider, how reasonable do you think it is that maybe somebody could create an infinite loop detector which generally works in all cases? At this point, you should feel like that is probably not even remotely possible, because if you had such an infinite loop detector, you would automatically be able to tell if my code here is going to stop, and that means you will have solved the perfect box problem, right? And in fact, it's not so hard to see that actually more or less any major unsolved problem in mathematics could be solved automatically if you had an infinite loop detector that worked in all cases, all right? If there was such a thing, it would basically make all of mathematics simple. Like you wouldn't have to have any kind of ideas about any perfect box. All you would have to do is run it through this infinite loop detector and it would solve the problem for you, all right? So let me just say, any general loop detector, like how sophisticated would such a thing have to be? The answer is very, very sophisticated. It would have to be at least good enough to solve the perfect box problem, which is a problem which has been unsolved for hundreds of years. It would also have to solve all kinds of other unsolvable mathematical problems. So any general loop detector would automatically have to solve, I would say, extremely hard. By extremely hard, I mean currently, like with current mathematics, unsolvable problems. All right. From this point of view, I hope that everybody would agree with me that such a thing is too much to hope for. And if that thing did exist, it would basically ruin mathematics. Like I, as a mathematician, I hope and pray that such a thing does not exist, because if it did, it means every time I ever tried to prove something, I could have instead just run it through this loop detector, and it would tell me the answer without giving me any insight at all. All right, any general loop detector would automatically have to solve extremely hard problems, and so maybe at this point it should not be a surprise to you. This is what sort of one of Turing's biggest accomplishments. So Turing proved that the general halting problem is what he called it, and that's, I suppose, what we still call it today. The general halting problem is unsolvable. So it is a fact, actually, there is no such infinite loop detector. You know, it now occurs to me I should cancel that program because it's still gonna, it's running very slowly now, you can see, because it has to be, it's checking an extreme amount of stuff. All right. The general halting problem is unsolvable. What that means in particular, it means for some procedures, well, I'm going to say more specifically, there is no general procedure to decide if some other, I'll say this in modern terms, if some other code will halt or not. This is the resolution of the halting problem. Turing showed that it is actually impossible to do this. And this is the first, historically speaking, maybe this is one of the first things that it was ever proven that no possible computer can ever do. So when I was talking, at the beginning today, there are certain hard limitations to what a computer can and cannot do. This is one thing that a computer cannot do. It is not possible to make a computer which is capable of looking at another computer and saying whether that other bit of code or whatever will halt or not. And this, I will just reiterate, I'm not saying we just haven't figured out how to do this yet. I mean, like, it's actually mathematically proven that that's not possible. There is no such thing as a computer which can tell whether or not some other code will halt. It's true. Anybody got any thoughts about this? I tried this with ChatGPT, actually. I like wrote some code, pasted it in, and said, hey, can you tell me if this is going to halt or not? And it said something like, I don't do that, or something. Like, in specific examples, it may be that the code is so simple that you can easily tell if it's going to halt or not. So I'm not saying that this problem, generally speaking, is never possible to do, but I just mean there cannot be a general purpose tool which will always succeed in deciding if a bit of code will halt or not. This is kind of interesting to me, although a little abstract, I suppose. If you tell your friends at dinner, hey, I learned today that there are limitations to all computers that exist and could ever exist. And they'll say, oh, really? What are the limitations? And then you spend like 20 minutes talking about halting, whatever, and they'll be like, let's talk about something else. It's a little abstract, right? But actually, there are more sort of down-to-earth things that you can demonstrate are similarly unsolvable, kind of like the halting problem is. Hey, we'll get to that stuff eventually. Any thoughts about this? I don't mean to, typically I don't like sort of standing here and talking for the entire class while you all listen, but I hope you don't mind for a little historical introduction. I think maybe I'm going to leave it at that. We got 5 more minutes on the clock, but I think that'll do it enough for today. Next time we're going to start like very, very much more sort of nuts and bolts, starting off with the real material for the course. We will eventually get back to the halting problem and see why. We're going to go through the basics of how to prove that it's unsolvable. It's not so hard. All right, please let me know if you have questions. Hopefully you can figure out the grade scope, those of you who are having issues. If not, tell me and we will work it out together. See you next time in a different room.